Okay, let's get started. Just a reminder that I'm not going to be here on Friday, but I will be posting a video of a lecture for you to watch over the weekend. Make sure you watch that before Monday's class, so you don't get out of learning more material. I will also, by the way, be gone on Thursday, so I won't have office hours on Thursday. So Thursday and Friday I won't be here. Wednesday, now there's an interesting situation brewing. How many people are hoping for a blizzard? All right, true North Dakota, right? You're not from North Dakota. Yeah, so keep your eyes out on the weather announcements. If we do cancel the school, which I don't expect to happen, but if they do, what should we do? Not go to class. I could post a video also. As a matter of fact, I think I will try to do that. If school does happen to be closed on Wednesday for weather reasons, I will post something. And I won't make it an hour long, so it'll be a little bit shorter, but something else for you to watch. Technology is great, isn't it? No breaks for you. And that's a good thing because there's a lot of material to cover before the end of the semester so that you can all be prepared for, I don't know, your MCATs and PCATs and all those kinds of things. So let's continue talking about alkenes. So if you recall from Friday, we talked about structure of alkenes and how this pi bond, side-to-side overlap, prevents free rotation. At least in order to rotate around a carbon-carbon double bond or any double bond, you have to break the pi bond to do it. So it's a high-energy process, or it can be done under certain kinds of chemical reaction conditions. But it does fix the geometry of substituents on a double bond in space. So although we haven't changed which atoms are connected, we can change their orientations in 3 dimensions because they're stuck in one position. So there is stereochemistry, stereoisomers available on double bonds which have different substitutions on the ends. So we talked about trans double bonds and cis double bonds. And we talked about the other kind of nomenclature for indicating the stereochemistry of groups situated on double bonds, particularly when all of the 4 groups are different, right? And we use these priority rules to assign the priorities based on atomic numbers for the atoms. And so if you recall, we talked about how to do that systematically. If 2 atoms on one side of the double bond are the same that's connected to the carbon, then you need to look at what those are connected to and go out until you make a distinction. If you have trouble with that, please do more problems on that. We talked about the fact that alkenes, just like carbocations and free radicals, alkenes are stabilized by the addition of substituents, alkyl substituents on the double bond, and that's due to hyperconjugation. So anytime we have any kind of p orbitals on a carbon, and you put alkyl groups next to it, you could always stabilize by interaction of bonds which could be aligned. And so this is true for alkenes. So alkenes which have 1 substituent on it versus 2 substituents or 3 or 4, they get progressively more stable or lower in energy. Okay, and finally, we talked about the fact that steric interactions, size of atoms bumping into each other, can also impact the stability of alkenes, particularly if those groups get larger. You can see just, if we just look at 2 methyl groups, that the difference between the cis-2-butene and trans-2-butene is significant. You get about a 3-to-1 mixture if you let that equilibrate. In this case, it's an acid-catalyzed process which allows that bond to break and reform. So we can see that thermodynamically that the trans isomer is more stable because that's formed in more amounts in this equilibrium. So it's a little bit lower in energy. And that's just due to the steric crowding that's involved. It's not a difference in substitution because they both are di-substituted, right? So if the groups get larger and larger, that energy difference between those 2 isomers will become greater. So keep that in mind also. Okay, well I want to move on now and talk a little bit more about alkenes. In particular, if you think about putting a double bond in a ring, you also have ring constraints to deal with. So I just said that because of steric reasons, trans isomers are more stable than cis isomers. But if it's forced into a cis conformation, it has to be the only one available. And until you get to a large enough size ring, it can only accommodate the cis orientation. If you think about a double bond, remember that a double bond is sp2 hybridized. So let's just take this cyclohexene, for example. Okay, it's sp2 hybridized, so that atom and that atom, they're both planar, right? So everything attached to it has to lie in the same plane. That will include this atom, and that atom, and that atom, and that atom. So all of those atoms are fixed in one plane. Okay, there's no bending or twisting that can occur. So if you tried to do this in a trans orientation, right, it wouldn't be possible. So if you think about it, how could you do, make a double bond here, a trans double bond with 6 atoms? Boy, I don't even know how you could connect this. You could have really weird, oops, that's too few. Anyway, you can see if we try to make a trans double bond in a small ring, there's no way you could have all of those atoms in the same plane and have the ability to connect them because they're on opposite sides. Okay? Actually, cyclooctene, I've drawn that up here. And that's an interesting one I'm going to talk about in a minute. If we think about what we know about 6-membered rings, recall that in a cyclohexane, the lowest conformation is a chair conformation. That's changed a little bit in the 6-membered ring. It has to accommodate those atoms that are all in the same plane. And here is how we draw the 3-dimensional conformation for a cyclohexene. Keep in mind that we have the 2 carbons of the double bond are in the same plane. That carbon is in the same plane. Those are going away from us. Okay? And coming out towards us, which I haven't drawn, are the hydrogens. And so if I doctor this up a little bit, you can maybe get a little bit of perspective. Notice if that double bond is cis, like it is in a cyclohexene, those can be in the same plane, but then the other 2 carbons can still join them in the back. If I were to bring this carbon out front, there's no way you could connect that ring up. But you'll notice that it does still adopt what we refer to as kind of a half-chair type of orientation. Now, because of the sp2 hybridization, it can't be a complete chair. This has to be all flat here. But it does twist, and it twists to try to alleviate some of those torsional strains. And we have on here substituents which are sort of pointed axial and sort of pointed equatorial. As a matter of fact, when we refer to cyclohexene conformations, we refer to these as pseudo-axial and pseudo-equatorial. So this would be a pseudo-axial positions here and here. And then the other ones would be pseudo-equatorial positions. They sort of mimic, they have some of the similar aspects of a cyclohexane in terms of the axial or pseudo-axial positions are more crowded than the pseudo-equatorial positions. And so a lot of the things we learned thinking about cyclohexane conformations do still apply in a cyclohexene that has 1 double bond in it. The only difference now is that we have this flat area where it's not a complete chair all the way around the ring. And it still can flip, by the way. There is enough give in this molecule that it could flip from one half chair to another half chair type of orientation. So you can still have these sort of the same kind of flipping of conformers that we have in cyclohexanes. Okay? Because of the ring, the double bond has to be the cis geometry until you get to an 8-membered ring. That's actually the smallest ring where it's possible to have a trans double bond, although it's still higher in energy. If you look at a cyclooctene, what I've shown here is cyclooctene. You could have a trans double bond, it could fit and still be connected by those 4 atoms in the back. So it's possible to have the trans double bond, although it is strained. It's more strained than the cis double bond simply because these bond angles tend to become much shorter. So you have a lot of angle strain when you have this trans double bond. And if you allow that to equilibrate, you see that the cis double bond is more stable by about 39 kilojoules per mole. As a matter of fact, the trans cyclohexene is not stable above, oh gosh, I forget the temperature now, something like minus 100 degrees or something. It's been detected at about a minus 100 degrees, but if it warms up any more than that, then it rapidly equilibrates to the more stable cis isomer. Once you get to about 10 carbons in a ring or more, then it becomes much easier to have trans double bonds present in a ring. But for the most part, we won't be dealing with those really larger cycloalkanes. But keep in mind that any of these sizes of rings that we typically deal with, 5-membered, 6-membered, 7-membered, 8-membered, they're going to be the cis orientation. So I don't want to see you drawing any trans cyclopropanes because it just wouldn't be possible. Okay, well, we've talked a lot about the structure, the stereochemistry requirements of this pi bond, but we really should talk about how we make alkenes. Okay, we are organic chemists, so we want to make molecules, right? And so we have to have a way to put in alkenes where we want them. So the reaction which we use to do that is referred to an elimination reaction. This is one of the main ways in which we have to synthesize double bonds between carbons. Going from a molecule which has all sp3 hybridized carbons, losing or eliminating an atom from adjacent carbons, so what I've generically put A here or B here. By the way, your handout says X and Y, and I didn't want to confuse you with X meaning a halogen because I don't necessarily mean that. This is more generic than that. So I changed that on my slide here. So if you remove an atom from adjacent carbons, and that would essentially form a new molecule or eliminate off A and B, and left behind is a bond between the carbons. So if you think about the electronics or where the electrons are and where they have to go for this, how might these atoms have to break off? Well, if you've broken a carbon A bond and a carbon B bond, and you formed a carbon-carbon bond and an AB bond, that means there's 2 electrons. Let me clean this up here. There's 2 electrons in this bond and 2 electrons in that covalent bond, right? And what we formed is a bond between carbons. There's 2 electrons there. That's a new bond, and then there's 2 electrons there. So obviously, if you think about it, when we break off those atoms, one of them has to come off with a pair of electrons, and one has to leave a pair of electrons behind, because one pair of electrons has to end up between the carbons. Okay, so this will come off. Let's say this comes off as an A plus and a B minus. So there's the electrons that form the AB bond. The electrons that were with the AB bond form the new double bond. And this is something which is general and consistent with all of our elimination reactions that we'll talk about. Okay, so let's look at some specific ones. So switch this back. Go. Okay, let's look at some examples. So one way in which we can do elimination reactions is to eliminate hydrogen from an alkane. Now this is not an easy process. As we talked about before, alkanes, hydrocarbons, are relatively inert, right? And they're stable molecules. As you can see here, industrially this could be done, but at temperatures of 750 degrees or higher. And actually these probably come off as free radicals, not as ions. But the point is that if you're making small alkenes, industrially, you could certainly make them through this kind of cracking or high temperature process. But it's only useful for practical reasons in small hydrocarbons like ethane and propane, because once you start to get longer chains and more complicated molecules, you form double bonds all over the place, and then you have all kinds of constitutional isomers. Okay? There's no way really to control which hydrogens come off in this process. But industrially, for making ethylene or propylene, this thermal formation of them from alkanes and petroleum products certainly is used and can be used for some of these simple molecules. But when we have more complicated molecules, we need more precise and more controlled ways to form double bonds between the carbons we want. So we need functional groups there that we can then eliminate and control. Okay? We've talked about alcohols. Alcohols, we saw we could replace an OH group for a halogen by reaction with something like HCl or HBr, right? But we also can do an elimination reaction. In this case, you can take an alcohol and remove a molecule of water, a hydrogen from one side and an OH from the other, form the new pi bond, and H2O is the byproduct here. Okay. This is a reaction which is done under acidic conditions, generally. So we have acid catalysts, just like we had acid catalyzed substitution, right, with HCl and HBr. With the right acid and conditions, we can do acid catalyzed elimination. So if we look at this, we're removing a hydrogen and we're removing an OH. What is your guess as to which one will come off as a positive ion, which will come off as a negative ion? Yes, you should hopefully know the oxygen is more electronegative. OH is going to come off as a hydroxide, so the element of hydroxide, and this is going to come off as the element of H+. Okay? Now, that's not to say OH minus just pops off of here. It doesn't. It's an acid catalyzed process which does this. So just like we talked about reaction with, let's say, HCl, what happens when we do substitution chemistry? You protonate the oxygen, right? And then that could come off either to form a carbocation or do an SN2 substitution. Well, the same thing is actually happening in this case. It's just that there's not a chloride or a bromide to add on to that carbocation. Instead, a hydrogen on a beta carbon adjacent to that comes off. I just threw another term that we often use in chemistry at you. When we talk about the alcohols, we refer to the carbon that is attached as the alpha carbon and the carbon adjacent to that as the beta carbon. Just the Greek symbols went away. So I might talk a lot about beta elimination or beta hydrogen elimination. That's just meaning the carbon adjacent to where the OH comes off. So in a sense, I kind of generalize these elimination reactions as having whatever's coming off as the, quote, negative ion, I refer to as the leaving group. And the adjacent to that is a proton on the beta to that leaving group. Okay? We're going to talk a lot of details about this reaction. I want to show you some examples, specific examples of this reaction and what's going on. So if you take a look at this, we have the reaction of ethanol, okay, reacting with sulfuric acid. And if you keep that up to 160 degrees, you form ethylene and water. Okay? Notice what happens if instead of ethanol, which is an alcohol and a primary carbon, I do the reaction with cyclohexenol. Now the OH group is on a secondary carbon. It's a secondary alcohol. Do the same reaction, heat it up with sulfuric acid, but actually the alkene starts forming at a little bit lower temperature, 140 degrees. And if I use tertiary butyl alcohol, now alcohol is on a tertiary carbon, the reaction is occurring below 100 degrees. So the more substituted the carbon is the alcohol's attached to, the easier the reaction is becoming. It's going at a faster rate. Okay, why do you suspect that might be?
The carbocation is more stable. These are in the secondary.
Yes. The carbocation, it's reasonable to conclude, based on all we've talked about in the substitution chemistry, that the mechanism has some similarities, where it must be forming a carbocation. The carbocation is more stable on a tertiary carbon, so that one's going to be the one that reacts the easiest. It's the exact same trend we saw when we looked at HCl or HBr substitution of the OH for the halogen.
So
okay.
The double bond is coming off.
So in all these cases, let me just show you what's happening. So in this case, the proton on the beta carbon and the OH group is coming off to form the double bond in the water, right? In the next case, I haven't drawn the hydrogens, but there are two hydrogens on that carbon. One of them must be coming off, and this is coming off to form the new double bond. Okay? And for the tertiary butyl alcohol, there's a CH3 group on each of these, so there's a beta hydrogen next to that alcohol on all of them. So, and each of those carbons are equivalent, so it really doesn't matter which methyl group you take the hydrogen off, you'll form a double bond connected to the middle carbon and then two methyl groups left. Does that answer your question?
But you know, you've got the double bond on this. Is that coming off of that in the product side of the reaction?
In the bottom one?
Yeah.
Okay. So we have a CH3 here, right? CH3 here, and CH3 here, and a carbon here. So this carbon the alcohol is attached to is that one right there.
Right.
Here's one CH3. Here's another CH3. The other CH3 has one of the protons removed.
There we go.
Okay, make more sense?
Makes more sense.
Yes, get used to line structures. Yeah, it's that connection between knowing where the hydrogens are and where the carbons are, so don't get confused by how I've oriented it.
Mm-hmm.
Okay, so there are some similarities to our substitution mechanism. Most likely the first step is protonation of the alcohol followed by formation of a carbocation. Okay, and that would explain that trend. There are some other aspects to this reaction. The elimination reactions generally form, if there's a difference, you can have possible regioisomers. Regioisomers, those are constitutional isomers. That is, the double bond could form from different carbons that are next to it. So if we take a look at this top case, we have an alcohol attached to a tertiary carbon. Okay, there are two CH3 groups next to it. Okay, those are equivalent groups. If you take a hydrogen off of any one of those to form the double bond, let's say between here and here, that would lead to this product. Okay, doesn't matter which one you take off; they're identical. You've taken off one hydrogen, and the other CH3 is still left. All right. If instead you take off one of the beta hydrogens on the other side of the alcohol, that's different now. It's not just a CH3. If you take off one of these hydrogens of the OH and form the double bond there, that gives you the product on the right. So depending on which hydrogens are available beta to where the alcohol is, you can form different regioisomers. Those are constitutional isomers because they're bonded differently. And so you hear me talk about this regioselectivity. Is how selective it is for forming one over the other. And selectivity in forming double bonds by elimination reactions generally follows the concept of forming the most stable double bond, preferentially. And this is, was observed by a Russian chemist named Zaitsev. And so he came up with his rule when he observed this, that says elimination occurs to form the most substituted double bond preferentially. That is the double bond which is the most stable one, right? The more substituted double bond, the more stable it is. We talked about that at the last class. So notice in this case, the product, which is the minor product, 10% of the product mixture has the double bond with 2 substituents on it, and the product, which is the major product, has 3 substituents on the double bond, 3 alkyl groups. So it's a more stable one. The same is case in this one. If we have this cyclohexanol, which now has an additional group, there are 2 places where you can eliminate a hydrogen on a beta carbon. So beta to the OH. Oops, that's not an OH. We're going to do that. That's a hydrogen. I'll draw them in for you for clarity's sake. If you're going to eliminate this OH group, okay, that means you have to take off a hydrogen on a beta carbon. There's a carbon here is beta to that OH group, and a carbon here is beta to that OH group. Those would give different products because the cyclohexane that the alcohol is attached to is not symmetric. Okay? So if you take off the hydrogen here, you'll get this product. And if you take off the hydrogen that's here, you'll form the double bond there, you'll get the product on the right. You see that? And again, what we observe if we carry out this reaction is that there's a preference or a preference in the reaction or a selectivity in the reaction for getting the double bond, which is more highly substituted. So if you look at the double bond, there are 3 alkyl groups attached to that double bond on the left. And the double bond on the right, which is here, has only 2 alkyl groups attached. So it's a di-substituted double bond. It's formed in less amounts. Okay? Again, the trend is you'll form the more stable double bond if you have a choice. It's not completely selective, by the way. You still see some of this as a minor product. That's why we refer to it as a selectivity. There is some preference for one over the other, but not complete control. And likewise, if you have a possibility of being able to form either a trans or a cis double bond, guess which one you form preferentially? The more stable trans double bond. Okay, trans double bonds are more stable because they are less sterically crowded. Let me draw the hydrogens in here so you can see cis and trans. So this is cis, this is trans. You get about a 3-to-1 mixture, just like you would if you were to equilibrate them. We talked about that previously for 2 butenes, right? Get about a 3-to-1 mixture favoring, again, the more stable trans double bond. In this case, this particular example, the alcohol is symmetric. You have beta hydrogens here, and you have beta hydrogens here. Okay? If you do either one of them, you're going to form a double bond between the middle carbon of this 5-carbon chain and a number 2 carbon. Just depends on which side you number it from. So you don't have an issue of regioselectivity. But you have a possibility of forming 2 different stereoisomers. This is what we refer to as stereoselectivity. Again, it'll eliminate to form the more stable transalkene. Okay. Any questions on that? If you can form more than one constitutional isomer, then there's an issue of regioselectivity. You'll form the most substituted one because it's the most stable. If you have an issue of being able to form a cis or a trans double bond, you'll form a trans one because it's also more stable. That's a stereoselectivity. Okay. Those are some of the details of the observations. When one carries out this reaction, those are the types of results that you see. So we need to rationalize those results in context of the potential mechanism or how the reaction takes place step by step. And I've already alluded to this, right? The mechanism for dehydration, which is the specific form of elimination where we're removing water from a molecule, goes through usually an intermediate carbocation. One clue to that, by the way, is if you're under acidic conditions, carbocations are very likely. If you're under basic conditions, trying to form carbocations will be very difficult. In this case, it's sulfuric acid. Sulfuric acid, as you can imagine, could react with this. The mechanism, which we refer to for this, the main mechanism is what we call the E1 mechanism. What do you think that stands for? Elimination, and what the 1 stands for? Unimolecular. Remember when we talked about substitution? If the protonated alcohol came off as water to form a carbocation, the rate determining step only involves that one molecule breaking apart. That's the slowest step. So it's a unimolecular reaction rate, or a reaction. The same thing in this case. It's an elimination reaction, which the rate determining step is unimolecular. Okay? So again, just like substitution, it's exactly the same. What happens first is a protonation of one of the lone pairs of the alcohol with the acid that's present. That's a fast and rapid equilibrium like we've talked about before. So in an E1 mechanism, let me just write it out here. Okay, so you have, let me use R. The oxygen, which is now protonated. Okay. That could then undergo bond cleavage, so the water will come off with those pair of electrons to form an intermediate carbocation, right? That's the high energy step, and I don't have the reaction energy profile here to show you, but just like in substitution chemistry, that's the high energy step, the lowest, the slowest step, the rate determining step, only involves that one molecule breaking apart. Now if I had used HCl or HBr, what would happen? The Br minus would add to that plus charge. Well, in fact, one of the differences between mineral acids of the halogens and things like sulfuric acid or phosphoric acid. Let me just draw sulfuric acid here. This is the Lewis structure for sulfuric acid minus all the lone pairs. What will you form if you take a proton off is a much more stable, less reactive anion. It's the sulfate anion. So if I were to take off this hydrogen and leave behind the minus charge, okay, that sulfate anion is not a very good nucleophile, and it doesn't add that well to things like carbocations. What happens instead of forming a new bond to where the carbon plus is that this proton comes off. So the electrons for the proton flow down, and so the sulfuric acid, or if there's water, the water molecule will grab that proton. That will regenerate your acid catalyst. So in principle, you really only need a catalytic amount of acid. And in that process, it forms the double bond. So up until this point, the mechanism is identical to forming an alkyl halide. But without halide present, it simply loses a proton, so the electrons can satisfy the plus charge on carbon and form a double bond. So you see the connections between the mechanisms. It diverges at a later stage in the mechanism. But the rate determining step is still the same. Okay? Like substitution reactions, this works to form a carbocation if the carbon of the alcohol is tertiary or secondary. So if those, what I've indicated as R groups there, are 1 or 2 carbons, that will always go through a carbocation. There are some examples, just like in substitution, where you don't form a carbocation, right? If you have a primary carbon, the alcohol's on a primary carbon, it's really difficult to form a high energy carbocation. So remember when we had HCl, what happened in that case? Let me just review this. So protonation would form the protonated alcohol. Okay. If it's on a primary carbon, I've drawn hydrogens there now. If it's on a primary carbon, it's harder to form a carbocation. If you had a halogen like chloride or bromide, it came from behind and kicked this off at the same time. It's a one-step process where you form the bond to the halogen at the same time that the water is leaving, that bond is breaking, right? That's the SN2 substitution, nucleophilic substitution bimolecular. Well, a similar thing happens here also. If we have a primary substrate where it's very difficult to form a carbocation, we can go by a mechanism which is what we call the E2 mechanism. Elimination, but the rate depends on two molecules. It's bimolecular. That second molecule in this case is the base. Could be a water molecule, it could be the sulfate ion. I'll just use sulfate ion. HSO3 minus, or HSO4 minus. Okay. In the rate determining step, the proton is being pulled off by that anion. At the same time, the double bond is forming and the water is leaving. So all of this is happening in one step. And it goes directly to here without forming a carbocation intermediate. That's an E2 reaction mechanism. Under acidic conditions, it's rare except in the case of primary alcohols. So when you can't form a carbocation, it will do it without forming a carbocation.
So this is bimolecular?
This is a bimolecular reaction because this is the slowest step and it involves two molecules, the protonated alcohol and either sulfate or water. It really doesn't, it can depend, or a base. Depends on both of those things. That's why it's an E2 mechanism. Okay? Is that clear on the differences between those? Again, for carbocation, for acid catalyzed chemistry, it's most often forming carbocations.
So,
oops, sorry, I just erased that.
Well, just like the E2 would be the best direction because it's the lowest energy.
E2 will only do, it'll only do E2 if it's a primary alcohol because forming the carbocation is very difficult. Okay? Trust me, it gets a little more complicated than this. Okay, now here's an interesting observation. So this tells you that the reaction has other potential pathways open to it. So if you take this example, okay, notice what I have here is an alcohol. There's the alpha carbon that the alcohol's on. Here's a beta carbon and here's a beta carbon, right? Only one of those has hydrogens on it. So if the reaction is occurring, like I said, you should form this product and put the double bond between the two end carbons because that's the only place that you can take a proton off. Right? You follow that? Okay, now here's the problem. When you carry out this reaction and you do this, heat this up with phosphoric acid, you see about 3% of that product. Okay? Two other products are formed preferentially. This one on the left is formed in 33%, and the one on the right is formed in 64%. What's happening? How could that be possible? Take a look at those products. What has happened in this molecule? The carbon skeleton has rearranged. Okay, we've actually moved a carbon around. So if you look at this product on the left, notice the alcohol was originally here. That's where the alcohol was. Okay, that alcohol was attached to a tertiary butyl group and a methyl group and a hydrogen. But notice it's now attached to a 3-carbon group and 2 methyl groups. Something strange is happening. The same thing here. If this is the carbon that the alcohol was originally on, This is a 3-carbon group, and then it's attached to 2 methyl groups. So somehow a methyl group has moved. This methyl group, one of these methyl groups on the carbon on the left, has moved over to this position. Well, this is a problem when you have reactive species like carbocations. Carbocations tend to undergo skeletal rearrangements. We actually break carbon-carbon and carbon-hydrogen bonds and move them around if it can form more stable carbocations along the way. So if you take a look at this, let me just make some room here to draw on. Okay, if you take a look at this and we follow the same reaction mechanism, what's the first step? Protonate the alcohol with the phosphoric acid. Okay? That would lead to this intermediate. I'm just going to say OH2. You understand that, right? Okay, that's the intermediate. Then that can undergo loss of the OH2 group. The water can come off, okay, to form our carbocation intermediate. Forgive me for leaving off the hydrogens for a moment. I'll draw them here. That carbocation intermediate, if you simply eliminate the hydrogen on the end, you'll get to the product, right? That explains that product, but that's a minor product. Notice the other products were moving of CH3 group. So what happens when you have this p orbital, a carbocation, the groups next to it are undergoing hyperconjugation, right? What can happen is this methyl group can shift over with its electrons and form a bond to that carbon. That leaves the carbonate left positively charged. So instead of just eliminating hydrogen, before that takes place, this is a faster process, and I'm running out of room. Let me draw it here. I'll draw it in blue so you can see. If that CH3 group moves over, you get that. Okay, this is the CH3 that moved. And why would it do that? Why would it bother doing that? Why would you break a carbon-carbon bond and move a CH3 group over?
Less sterically crowded.
Not less sterically crowded. The most important thing is that this is a secondary carbocation here. And by the CH3 moving over and leaving the other carbon empty, we now have a tertiary carbocation. It's a more stable carbocation. So this is what's referred to as a carbocation rearrangement, or a methyl group shifting from one position over to a carbon. This happens when it can form a more stable carbocation. If it doesn't form a more stable carbocation, you're not going to break carbon-carbon bonds. But if it can shift over one and break and then make a more stable carbocation. If you go from a primary to a tertiary, or primary to a secondary, or secondary to a tertiary carbocation, it becomes more stable and it gets better. So once you put the carbocation there, then you have the ability, let me see if I can't clean this up a little bit. We just take a look at this intermediate. Then those two products are easily explained by elimination of this proton to form the more substituted double bond. Okay? Or you can eliminate one of these protons to form this double bond on the end here. Okay? And it's not just carbons which can shift. Hydrogens next to it can also shift around. So those are the two products. And here is showing the energetic difference and why this happens. Remember that groups that are adjacent to a carbocation, that empty p orbital, like this carbon CH3 bond here, that carbon CH3 bond is aligned up in the same orientation as the p orbital. That's why it could shift over. In the transition state, it's shifting over, and notice a new p orbital is forming on the carbon it's leaving. And the p orbital on the carbon it was on becomes a new sp3 orbital. Okay? Going from a secondary carbocation to a tertiary carbocation, you go lower in energy.
So when this happens, when you're shifting,
Yes.
It's a fairly fluid process.
Yes.
So you're going to have a larger amount going to forming the carbocation on the secondary carbon, and but then you're also going to have the substitution happening also along.
So yeah, so when you're doing these kinds of eliminations and you form a carbocation, the carbocation, if it can rearrange to become more stable, it will do that faster than loss of the proton to form the double bond. And that's why most of the product occurs from the carbocation after a methyl group rearrange. So we only saw a little trace of this. Of course, a little bit of this could react just to eliminate to form the double bond, but most of it rearranges before that happens, and so that's the major product. So once you get to this more stable carbocation, then you can eliminate in a couple of ways to get two different radioisomers of that one. Okay, here's an example of a hydride shift. So notice this substrate that I'm showing, this particular alcohol is exactly the same, except instead of a CH3, we have a hydrogen there. Hydrogens are a little bit easier to shift than CH3, so if it's available, the hydrogen can also undergo a shift, which we refer to as a hydride shift. The hydrogen with its pair of electrons hops over. Okay, and again, this only hops over one position. So if it can become more stable, if it can go from a secondary carbocation to a tertiary carbocation, that hydrogen will move. If no hydrogen is available, like we saw in the previous slide, a carbon can move. Okay, and that can lead then to elimination either here or eliminating this way to form a couple of different radioisomers in the next step. Even if it doesn't form a full carbocation, it has been observed in some cases. If you have a primary alcohol, you protonate that primary alcohol, and if you have you could do an E2 elimination if you have the base take it off, but the hydrogen, and I should have highlighted here, sorry, I left it off. That hydrogen that moved over is right there. So this hydrogen could hop over and leave a secondary carbocation, even though it didn't form the primary carbocation to begin with, but it happened at the same time that the water leaves. That's also possible. So even if it's a primary and you think, well, there is no carbocation, things still could rearrange to form a carbocation. So this is what some of the complicating features of this process, that rearrangements can happen whenever we're talking about positively charged species like this. Okay, but for the most part, it happens very readily with free, when you form carbocation intermediates, secondary rearranging to become tertiary. And that's probably the most common type of rearrangement. It can happen with all kinds of substrates, not just a methyl group. If you have even larger groups or rings, you can make rings bigger and smaller by rearrangements and things like that. So some of the problems, I think, also allude to that as well. So hydride shifts. Let's see, we need to see what's next. And we can also do elimination of halogens. So I talked about loss of water. What I'm going to follow up on Wednesday is the similar process of removing a hydrogen and a halogen. So you can actually take an alkyl halide and eliminate HX from that to form a double bond. These are usually done under strongly basic conditions, so the mechanism is a little bit different.